Welcome once again to the next lecture for Geotechnics 254. And today we're going to look at soil and water interaction. Professor Tony Brink once said to me, no matter how much you've read or heard about a site, if you have not seen it personally, you know nothing of it. And that's quite a strong statement, but I'm giving you this advice that often your clients would try and prevent you or not pay for a reconnaissance visit. A reconnaissance visit can be as little as 15 minutes on site. But then when you look at the available data and your desktop studies, and when you go back to the site the next time, you have a much better understanding and you will be able or should be able to deal with the problems because your brain has been working on it. Just for interest's sake, this picture I took just outside of Barberton on the road to Eswatini, which used to be Swaziland. And here you can see a drainage channel on the side of a mountain that had been filled up by new sediment over time. So if you would dig a test pit on this site, if you dig it in the middle of the channel, you will think that you have a deep soil profile. But if you dig it on the either left or right edge, you will think you have a shallow soil profile. But looking at things like this in road cuttings, you will already now have the idea you may have areas of deep soil and areas of shallow soil, and you can prepare for it in your investigation as well as your site development. As I said, we're going to look at the interaction between soil and water. And so let's look at this picture. The top picture, as the water precipitates from rain clouds, some of it flows down into the streams, rivers, and eventually end up in the ocean. Some water, however, seeps down into the water table. The surface of the water table is termed the phreatic surface and is at atmospheric pressure. On the picture you will see a little diamond, upside down triangle at the water table. That is the internationally recognized symbol to indicate water table. In the middle part, you can have a perched water table which can occur where lenses of impermeable material are present in a profile. For instance, a clay lens in a gravel horizon. Then in the bottom picture, groundwater can also be confined under pressure in an ordinary sub-artesian or artesian condition if an impermeable layer is overlying the water-bearing layer. If a pipe is inserted into the water-bearing layer, probably a sandstone or sand, the water will rise in the pipe up to the level of the water table. However, if the water table is inserted in the impermeable layer, the water will rise not above the water table, whereas if the water table, the piezometric surface, is above ground, as in the last part of the picture, you will have a so-called artesian well. The water will come out of it automatically without the need to pump. If we look at the soil structure, we have hygroscopic moisture around the soil particles. Then we have adhered moisture film, and then in the corners, the so-called pore corner moisture. So if you look at the picture, above the groundwater table, the water can be held in a soil through capillary action, and it will be at a negative pore water pressure. In other words, it's basically sucking. The water is held back. The smaller the voids in a soil, the higher the horizon of saturation can rise due to the capillary tension. Above the zone of the groundwater is the zone of capillary water, and above that is the zone of aeration or aeration, where partial saturation occurs due to the water being held by the particle surface forces as shown in the top of the picture. So above the water table there is negative pore water pressure or suction, and the pore water pressure at the water table is at 0. And then the pore water pressure increase below the water table. So I'm going to go through a little example. At 2 meter depth or minus 2 meter depth, minus 2 meters below surface, what is the U, the pore water pressure? The U pore water pressure is the the unit weight of water times the depth. So the unit weight of water is 10 kilonewtons per cubic meter times 2. So the pore water pressure at 2 meter depth in this case is 20 kilonewtons per square meter. When the soil dries out, the pore water pressure goes towards negative, and then it tends to go back to 0 when the soil dries out. So if we take this example, the red layer, let's say it's a layer of soil, a permeable layer between impermeable layers. If we insert a small pipe into the soil, the H is the total head, U is the pore water pressure or the pressure head, Z is the height above the datum or the elevation head, and the datum can be chosen anywhere you want, but you always try to make it as convenient as possible. And then gamma W is the unit weight of water, and the pore water pressure divided by the unit weight is called the pressure. So Bernouli, and we're going to see multiple names from now on that all have different expressions that will help us in the future. He said the total energy is the potential plus or minus the pressure plus or minus the kinetic energy, where the H is the total head, as I said before, in meters. U is the pore water pressure or the pressure head. Z is the height above the datum, which gives you the elevation head. And then V squared over 2G is the kinetic energy, but it is basically 0 for soil. So H is the height above the datum to which the water will rise if a small pipe is inserted into the tube, or in our case a soil layer, at that point. So H is the height above the datum to which the water will rise. Let's go back to this picture. So H is the top of the green bit. The green represents water here, and that's to where the water will rise based on the pressure. So another example, we have a little pipe into sand. We have a water table 1 meter below surface, and it's saturated, and then where the little crosses are shown, these are the impermeable, fully saturated layer and the soil. So there's soil, and then saturated, there's water, and then the soil. Now, let's rephrase that again, sorry. There's the surface, and the water table is 1 meter below surface, and the saturated, fully saturated area is 3 meters deeper. So based on datum 1, so let's choose datum 1 at 2 meters below the depth of the pipe, and then so the head at A will be U over gamma water plus Z, and so it will be the 3 meters below the water surface and the 2 meters to the bottom of the pipe, which will give you 5, and then Z is 2 meters from the datum up to the bottom of the pipe, so the total head in this case is 7 meters. Whereas in the second case, if the datum is placed at level 2, then you have the same conditions. U over gamma water is still 5 meters, but your Z is now, the end of the pipe is minus 2 meters below datum 2, and therefore the total head in this case is only 3 meters. The flow velocity of water through soil is dependent on the soil type. The flow velocity is dependent on the soil type. So a silt will have a slower velocity than a gravel. In other words, gravel allows water to flow through much faster than a silt. Darcey is another guy that we will meet. Darcey's law states that groundwater flow velocity is a product of the coefficient of permeability, K, and the hydraulic gradient in that particular soil. So the velocity measured in centimeters per second equals the coefficient of permeability measured in meters per second times I. Or put differently, the velocity is K times I, where I is the hydraulic gradient. It is the difference, it's equal to delta H over delta L, and the head loss is what this represents, is the difference between 2 points, or the distance between 2 points. If you look at the picture again, the original picture of the red soil, the head loss between the first pipe and the second pipe is represented by this delta H over delta L. It's change in height over the distance. So Q, which is the flow rate, is the volume of water flowing per unit time. In other words, it's groundwater velocity times the area through which it flows. Q is therefore the VD, or discharge velocity, times the area. But groundwater velocity is very hard to determine, and therefore we say the flow rate Q is equals K times I times the area. So K is the important coefficient, so velocity is K times I. Q is equal to velocity times A, and Q is also K times I times A. Different ways of saying the same thing. So water flows through the connected pores in a soil. So Vs, the seepage velocity, is equal to the flow rate divided by the area of the voids. But the area of the voids is very hard or too hard to determine, and therefore we say the discharge velocity equals Q over A. Discharge velocity is equal to Q over A, and that leads us to the so-called discharge velocity triangle. And now if you want Q, it's velocity, discharge velocity times the area. You want the area, it's Q over discharge velocity, etc. And then the structure of the soil and sand affect the coefficient of permeability K and the flow path through the water. The temperature can also affect the K value by affecting the viscosity of the water. So essentially what I'm trying to show with this picture, if you have sand, the water will flow quickly down the sand into the clay layer, and then it will go slowly along the fissures in the clay, and then when it gets another opening to sand, it will go through the sand very quickly.